Good morning everyone, I'm Mr. Upra. I hope you guys enjoyed my previous session on systematic review, how to conduct systematic review. Now I'm going to teach you today the meta-analysis topic, and the aim of this teaching today is to understand the key differences between a systematic review and a meta-analysis, and data pooling methods, forest plots, and importance of heterogeneity testing. The learning outcomes of today's tutorial is to understand the key differences between systematic review and a meta-analysis, and data pooling techniques, forest plots, and meaning of heterogeneity and its importance, and methods of meta-analysis itself.
So what's the difference between a systematic review and a meta-analysis?
That's a good question, Artemis. So the key difference is mainly about the qualitative synthesis and data pooling. So in a systematic review, you assess the quality of studies and do a critical appraisal, whereas in a meta-analysis, you do data pooling and you do heterogeneity testing and do a statistical analysis in detail. The key steps in a meta-analysis is identifying the subject of interest, followed by constructing a search strategy, extensive search strategy in various databases using various search engines. So once you retrieve all the citations, relevant citations, you go through all the abstracts and develop inclusion-exclusion criteria, and then include the studies which qualify your inclusion criteria and which are relevant to your subject of interest. And then you do a quality assessment of the included studies. If they pass your quality assessment, then start doing data synthesis. And once you've done the data pooling and statistical modeling, you can analyze the data. And finally, writing about the results. So these are the steps. The key steps are identifying the subject of interest, database search, data synthesis, analyzing the data, and writing up results.
Dr. Malik, is qualitative synthesis the same as heterogeneity?
Not really, Yusuf. So qualitative synthesis meaning is you are assessing the quality of included studies, whether they report the primary outcome in a way it is required. For example, if you're looking at the mortality figures, whether you got level 1 evidence in that paper suggesting that the mortality outcome is so and so, or is it bad evidence, is it poorly conducted study. So that is what is qualitative synthesis. Whereas heterogeneity testing is to look at the numbers of all the included studies in terms of demographics, in terms of all the variables, looking at the variance among both rows and columns to see if this is meta-analyzable. So it's a data crunching. Heterogeneity testing is to see if the data can be poolable or whether we can do a pooled estimates. But qualitative synthesis is just clearly looking at the quality of the included studies, whereas here we are looking at the quality of the data of the included studies which have passed qualitative synthesis already, qualitative analysis already. Data synthesis. Data synthesis has got some steps. Number one is, like systematic review, you do qualitative evidence synthesis in the first place and then started extracting the data and pull the data onto Excel sheets, and then start cleaning, which is called data cleaning, and then reorganize according to the statistical models, which is data reorganizing. And finally, identify the distribution of the data before you run any tests. And once you identify the distribution of the data, then you do a heterogeneity test. So the key steps of data synthesis is qualitative evidence synthesis, data pooling, data cleaning, data reorganization, distribution of data to be identified prior to doing a heterogeneity testing. So these are the key steps.
Is data pooling the same as data extraction?
Data pooling, although it sounds like as if it is a data extraction, data pooling and data extraction you can use as a synonyms but not necessarily the same. There is a reason being, data extraction is nothing but you're plugging in raw data from the papers, exactly extracting the raw data and plugging into Excel sheets. But in data pooling you can actually combine various variables as well, which is like a kind of statistical modeling and reorganization. So rather than, you may not actually get you may have been reported you may get the data as if it is being reported as a percentages. Then when you extract and then convert into actual real numbers, then it becomes data pooling. So not necessarily the exact raw figures from your paper, rather you convert into meaningful pooled methods.
So what exactly does data cleaning mean?
Data cleaning, that's a good question. Data cleaning means like when you extract the data, raw data, people sometimes leave the numbers and words together, maybe sometimes full stops, commas, everything as it is. So each cell should have only either numbers or words. You can't club both categorical data and numerical data into one cell, because when you put it into statistical software, it doesn't recognize. So you need to separate the numbers and words. And actually, if you have a categorical variables, you need to convert into numerical variables and code them. So that is what is data cleaning is.
Dr. Malik, why do we need to identify the distribution of the data prior to statistical modeling?
That's an interesting question, Yusuf. So the reason why we need to identify distribution of the data prior to conducting any statistical analysis is, number one, if we do not identify distribution of the data, it is difficult to do a statistical modeling, number one. Number two is, in a meta-analysis, we assume that the data has got parametric type of distribution. So therefore you can pool them. But if your assumptions are wrong in the first place, if you pull up all the data which has got non-parametric type of distribution, there is a danger of encountering heterogeneity when you do heterogeneity testing. So you need to see what type of studies you can club. So therefore, it is important to identify the type of distribution of the data before even combining them to do a meta-analysis.
Is it always necessary to perform heterogeneity testing?
Yes, because heterogeneity will result in a spurious results, either overestimation or underestimation of the pooled estimates. So heterogeneity means there is a variance among the included studies. That means there will be variance among the outcomes reported as well. So some studies would have reported 5% mortality, some studies would have reported 30% mortality. You can't club the data which has got so much variance. So when there is a huge variance, then obviously the pooled outcomes and their pooled estimates will not represent actually true estimates. So there is a lack of accuracy. That is why it is important to test heterogeneity in a meta-analysis. Data pooling. The Cochrane methodology of data pooling has got 4 components to it. Number 1 is matching. Number 2, stratification. Number 3, modeling. Number 4, combining of the studies. So here is an example of pooled data which I published recently. This is a data of a diagnostic accuracy study where CT virtual colonoscopy is compared to colonoscopy. These are the studies included. On your left hand side, the studies included, author and year. That column has got study name, first author and the year of publication. In the second column, you can see the total number of participants reported in that or published. And then total number of polyps reported in that paper, which are under surveillance. And then you can see time period of surveillance, how long duration, like 1 year, 2 year, 3 year, 5 year. And then in the other column, number of polyps progressed to become advanced adenomas. And finally, the last column has got number of polyps progressed to become cancers. So this is an example of pooled data. But you can see there is a problem in this distribution of the data. So before I go in depth about distribution of the data in this table, I would like to talk a bit more about what type of distributions normally are. The forest plot, you can see it's a beautiful graphical representation of all the included studies. You can see in one picture, you get all the studies on your left hand corner, and then a graph itself in the center, and then their estimates, individual estimates with their confidence intervals, 95% confidence intervals, showing how each study differs from each. And also each study has got its own line, a rectangle with a line. The longer the line of a study, wider the confidence interval. And also the rectangle of each study, whether it is touching the red line. If it's touching the red line, that means it's contributing to the pooled diamond. So it tells a story. A forest plot is a graphical representation of all the included studies with their individual estimates and confidence intervals and pooled estimates, and finally heterogeneity statistics. So in one go, you will know that whether this is a good result or bad result.
If we encounter heterogeneity, what should we do?
That's a good question. If you encounter heterogeneity, where we say above 50% is a substantial heterogeneity, then obviously we need to look for the sources of heterogeneity, whether clinical or methodological heterogeneity, and then drop those studies and to see if the heterogeneity can be corrected or if the statistical heterogeneity can be reduced. See, I dropped few studies here, then the heterogeneity I-square value is dropping compared to previous slide.
So are ROC curves the same as the forest plot?
That's really good question. So I showed you SROC, summary ROC curve, and now I showed you forest plot of sensitivity and specificities. So you can see in the ROC curve, there is a pooled diamond, which is in red color, representing accuracy. But an ROC curve doesn't give the pooled estimate of sensitivity and specificity in the pictorial form, although there are values represented, but there is no pictorial form of pooled sensitivity and pooled specificity. Whereas here in the forest plot, it was opposite. There is no pooled diamond for accuracy here, but whereas there is a pooled diamond for sensitivity and specificity. So in ROC curve, the picture is mainly representing pooled accuracy, whereas forest plot is mainly representing pooled sensitivity and pooled specificity. So these are two different graphs, but both graphs have same meaning in a meta-analysis, which is they talk about pooled estimates like accuracy in ROC, pooled sensitivity and pooled specificity in forest plot. So I'm going to show you another forest plot where I included those studies within the 95% confidence contour in the ROC curve. So there are only 4 studies which are within the 95% confidence contour, if you remember, in the ROC. So the same studies, I did a pooled sensitivity and specificity. You can see that there is a drop of so many studies, about 5 studies. And so only 4 studies are left. And then the sensitivity, pooled sensitivity is also dropped to 73%. And pooled specificity is also dropped to 76%. But you can see some miracle happened. When you included those studies which are within 95% confidence contour in ROC, the heterogeneity while testing sensitivity became 0 completely. That means that the sensitivity results are 100%, take it granted that this is 100% true estimate. That means the pyruvate kinase M2 enzyme testing is sensitive up to 73% and accurate up to 80%, as you've seen previously in my SROC curve. So, but I would like to say that I couldn't deal with heterogeneity on the specificity side. You can never actually get rid of heterogeneity in both aspects completely. But we have to accept this as a final plot showing the summary of the estimates of sensitivity and specificity, because at least we could able to reduce the heterogeneity on the sensitivity side, which is what PKM2 require. Any screening tool requires high sensitivity and high accuracy and optimal specificity. So I would like to therefore report that the PKM2 sensitivity of the test in sensitivity of the PKM2 test in diagnosing colorectal cancer is 73%, accuracy is 80%, and specificity is 76%. But I'm confident in reporting sensitivity and accuracy, but I am optimistic in reporting specificity because of heterogeneity. So this is my final plot.
So you said this is the final forest plot. Can you summarize the results, please?
Yes, so to summarize the forest plot results, how we summarize is total number of studies which are included in the final analysis are 4 studies, as you see on the left hand side, and their sensitivities reported with their confidence intervals, and also pooled estimate which represents pooled diamond, and there is a Q coefficient from chi-square test, and also I-square which is calculated from Q value which represents heterogeneity, and also P values for heterogeneity testing. And also you can see on your right hand side same measures like all the 4 studies with their specificities, individual specificities with their confidence intervals and their Q values and their I-square values. So here you can clearly see there is a pooled estimate of both sensitivity and specificity with their heterogeneity statistics. So therefore, you can translate these values into real-time practice if there is heterogeneity encountered is less. So I can take from this graph sensitivity as a true estimate of the pyruvate kinase M2 enzyme and can translate this into practice. So sensitivity of PKM2 is 73%. Specificity, I need more data before I can report it because of heterogeneity. So to summarize results of my meta-analysis, I gave you SROC, I gave you forest plot as my combined results.
Can the regression equations be part of meta-analysis?
That's an interesting question. I haven't shown you any regression equations in either summary ROC or a forest plot. Yes, when you can't do SROC or a forest plot because of heterogeneity, the next step is a meta-regression. Is also a type of meta-analysis, but only when you fail to do a forest plot because of heterogeneity, you then go on to regression equations, which is nothing but meta-regression.
So why do we need to derive a pooled estimate to perform a meta-analysis?
That's an interesting question again. So why did we need to get a pooled estimate? That's an interesting question. So why can't we just take a face value of each study? Is that what you're asking me?
Yeah.
So yes, you can see that the face value of each study is different. Like, Abdullah et al. Is reporting a different sensitivity. Hogg et al. Here is reporting a different sensitivity. So each study is reporting different sensitivity. So which sensitivity is the actual sensitivity of a pyruvate kinase M2 enzyme here? I'm confused. Therefore, I would like to take the pooled sensitivity as a final accurate measure of a pooled estimate. I'm going to show you a different technique of removing studies which are outliers. So I've shown you, if you do a summary ROC curve, the studies which are outside the 95% confidence contour can be removed so that all the studies which are within the 95% confidence contour are homogeneous. Likewise, there is another technique. So you can do a box plot, beautiful box plot, and to see if any studies outside the 95% confidence box, you can remove them. And so the studies which are within that 95% confidence box are homogeneous studies, deemed homogeneous. So with those studies, again, if you give a forest plot, you get low heterogeneity. So that is another technique. So this is a box plot which I'm showing you on the screen, which has got studies within the 95% confidence box and which are outside the 95% confidence box. And if I remove the studies outside the 95% confidence box, you can see the next box plot how it looks like. In this box plot, you can see I removed some studies which are outside. Now you can see only 4 studies are within the 95% confidence box and 2 are outliers. So it clearly says which studies are outliers. Therefore, you can drop them into your pooled analysis. So you will only construct a forest plot with those studies which are within the 95% box plot. So with that, I would like to conclude this session if you don't have any other questions.
So why do we need a box plot?
Yeah, see, there are so many ways of identifying the outliers. From the beginning, I was showing you goodness of fit test, SROC, and I haven't shown you funnel plots or box plots, but the best models where you can see the outliers is, number 1 is a goodness of fit, number 2 is SROC curves, number 3 is a box plots. So the box plots gives us a clue which are within the 95% confidence intervals and which are outside 95% confidence interval. So the studies which lie outside the 95% confidence intervals does not contribute to pooled outcomes or pooled estimates. Therefore, a box plot, unlike SROC, is another different methodology. If you don't want to present an SROC, this is an alternative solution to construct a box plot and see which are outliers. You can also do a funnel plot, but ideally we should do either SROC if you're looking at diagnostic accuracy or a box plot. So with this, I would like to conclude my meta-analysis session. I hope you enjoyed me representing forest plots, SROC curves, box plots, goodness of fit models. Please visit my demos to see how I construct all these plots. Thank you.